So welcome to the session 4 of live interactive sessions. So we have already finished 4 weeks in this course. So week 5 content and assignment are uploaded. So the assignment 3 solutions are released because the deadline was over. So I hope that you have seen the solutions of assignment 3. Right, so the feedback form for week 4 is also uploaded. So I encourage you to fill this feedback form. Okay, so one more thing I would like to point out today. So I have seen that a couple of you have requested for partial marking in assignment 3. So there has been response. So I think NPTEL is saying that there is no partial marking for MCQs. You have to get all the correct options ticked to get full marks. Uh, Otherwise, you don't get any marks. So I don't know whether uh, the assignment will be re-evaluated or not, but we'll wait for NPTEL to take a call. So other thing is some time ago, uh, there was a request for sample problems. So I had put up that request to the NPTEL team, and NPTEL team has responded in this way. So they're saying that if the learners want to solve more questions apart from the weekly assignments on the portal, they may solve exercises from the textbook Parameterized Algorithms or solve previous year's NPTEL assignments for this course. So it means that you can go to the textbook. So this is the textbook Parameterized Algorithms. And here at the end of each chapter, for example, now in the last week, we have seen chapter 5. So if you go to, let me check the page number. So assignments of exercise of chapter 5, right? So these are the questions you can see, and the questions are also sort of marked using, so this mark means very difficult question. This is a simple question. So they have been categorized also. So you can solve these questions from the exercises of the textbook. So other than this, the other option is you can join. So this course Parameterized Algorithms was also offered last year. So there is a course page for the last year's offering. There you will find some assignments and their solutions. So you can join the classes. So okay, I'm not logged in. Let me log in. Okay, now I'm logged in. So if I go to my courses, I can see that in the completed, why is it not showing? There seems to be some problem. Okay, let me refresh the page. So I have actually joined the previous year's course also. So this is the offering. So this is a previous year's offering. So if you can go to this course, then you will be able to see that all the week 2, week 3, week 4 assignments and their solutions are there. So I'll encourage you to join this previous year's course. So that is what the suggestion from NPTEL team is. Okay, fine. So this is all I wanted to say about the queries that you had raised. So now we'll go to the whiteboard again. Right. So in week 4, we have seen the randomized methods in parameterized algorithms. So these are some sample problems which I have picked from the previous year's offering. So we'll solve these questions, and I hope that solving these questions will help you solve the questions that are asked in this uh, assignment 4. Okay, so these are related questions. So let's go to these questions. So what I'll do, I'll make some space. So this is the first question. This is question 1. So you're able to see the question, right? Or shall I make it slightly bigger? Okay, so it is the question has 4 options. So you have to choose the correct option. So before we go to this, let me just rearrange the other questions. So I think this much space is sufficient. So consider an algorithm A that correctly identifies the no instances, but identifies the yes instances with high probability. Okay. So what does the algorithm do? So let us say this is our algorithm. This is a black box algorithm. Algorithm A. So if you give it an instance, which is a no instance, then you're asking, what is the algorithm's job? The algorithm's job is to identify uh, whether the given instance is a no instance or it is not a no instance. There is a yes instance. So if you give it a no instance, it is able to say correctly identifies that the given instance is a no instance. Okay, but if you give it yes instance, so let me copy this, or I'll just draw once again. So if you feed this algorithm a yes instance, then with high probability, so let us say with probability 1 minus epsilon, epsilon is a very small number. So with probability 1 by epsilon, reports that the given instance is a yes instance. Okay. But with a small probability, which is epsilon, reports that a given instance is no instance. So it makes an error, but with a very small probability. Now this is given to you, and you have to tell me that which out of these 4 options, or if there are multiple options correct, that is also fine. So which are the sort of correct options for this question? So what do you think about the first option?
So it seems that here B and D are true and A is not true as such. B and D
Okay.
are true. Yeah.
So these two are true, fine, and these two are false. So this one person has voted for B and D. So are there any more thoughts? So the what is the first options? First option is saying that if A returns yes, the problem instance is a yes instance. Okay. So the first one is saying that on the right hand side, the algorithm is saying yes, that yeah, this is a yes instance. So if it has said yes, then definitely the given input was an yes instance. The second option is saying that if the algorithm is saying no, if A returns no, then the problem instance is definitely a no instance. Okay.
So I would like to make a change here that A is also true.
Okay. So you're saying that A, B, and D are true.
Yes.
So can you justify why you are choosing these options?
Because see, if the algorithm is returning yes, so clearly the instance has to be a yes instance. It cannot happen that the algorithm is returning a yes for a no instance. That cannot happen. So, and in the second case, if algorithm is returning a no, then clearly the problem instance is a no instance because algorithm always returns the correct value for the no instance. And however, if the algorithm is if the problem instance is a yes instance, the algorithm may it is not necessary. It may return no as well because it is identifying the yes instance with some probability. But if the problem instance is a no instance, then the algorithm will always return yes. So I think that this algorithm is correctly classifying the problem instances in one side correctly.
All right. All right. Uh, so I agree with most of what you have said. But let's look at the options one by one. So first, let us satisfy ourselves whether the first statement is true or false. So the algorithm has returned yes. Sorry, yes. So the algorithm has returned yes. So this implies that the problem instance is a yes instance. So when can the algorithm return yes? So if it is a no instance, then definitely it will say no. The algorithm is saying yes. That means, so let us say for the sake of contradiction that I'll just make some space. So let us say use a different color that algo says yes, but the problem instance was no instance. So let us say, so this is for the sake of contradiction. Okay. So is it possible that we have a no instance and the algorithm is saying yes? So it is clearly said, the rule is clear that for any no instance, the algorithm will definitely say that it is a no instance. So our assumption is not true that if A says yes, but the problem instance was no instance is not possible. So therefore we have a contradiction. So therefore this cannot be true. It means that the opposite is true. That is, if algorithm is saying yes, then the problem is definitely an yes instance. So this is true. So is that clear? So proved by contradiction.
Yes.
Okay. So let us now look at the second question. So again, so the algorithm has returned oh, no. The problem instance that means that the problem instance is no instance. So let us say, for the sake of contradiction, that algorithm says no instance, but the problem instance is a yes instance. Is that possible?
Yes, that is also possible.
Yes, so that is possible. So we are not able to show any contradiction. So if you have a yes instance, there is no guarantee the algorithm is going to say yes, but with high probability it will say yes. But there is a small probability epsilon with which it might say that it's a no instance. So we are not able to derive a contradiction. Then how shall we prove that this is a true instance?
Could not hear you. Can you please say it again?
No, no. So you understand that this contradiction argument is not going through.
Yes.
We're not able to get a contradiction. So if
Mhm.
we assume something to the contrary, then we are not getting a contradiction. In fact, you may observe uh, that the algorithm might return no. So algorithm might say no, but there is that no may be corresponding to some yes instance.
Yes, that's possible.
Yes. So if the algorithm is saying no, there is no guarantee that the problem instance is a no instance. So this is not true. Okay. So let's move to the next one if you are convinced. So let's move to the next one. So next one is saying that if the problem instance is a yes instance, then necessarily A returns that it's a yes instance.
No, this is
That is
not necessary.
this is not true. This is immediate. This is from this rule that
Ye-
yes may give no. It's a very small probability, but still it is possible that it can give no. So this is not true. Then we'll go to the next one. So that if the problem instance is a no instance, then necessarily A is going to report that it's a no instance.
Yes, this is correct.
This is definitely true because that is the rule. The algorithm is correctly identifying all no instances. That is the first rule. This one is true. Okay, so are there any doubts on this question? Anybody? All right. So let's move to the next one. Actually, I'll make a new page. This font is large enough, I believe. I mean, there is no other. That's the maximum space we have on this tablet. I'll make it even larger. Right, so this is a long question. So I will. So let us read this question. Spend a minute or so in understanding what the question is asking. So in the tree subgraph isomorphism problem, we are given an undirected graph G, a tree T on K vertices, and the objective is to decide whether there exists a subgraph in G that is isomorphic to T. Okay. So let us understand what this means. So there is this tree isomorphism, tree subgraph isomorphism, sorry. This is a problem. It takes as input an undirected graph G and a tree on k vertices. So the number of vertices of T is k. And the question we are asking, the question this problem is asking is, does there exist? This is the symbol for does there exist? Does there exist a subgraph of in G which is isomorphic to T? Okay, fine. So everyone understands what is isomorphism. It was probably discussed in the videos. So for the purpose of this question, even if you don't understand what is isomorphism, that is fine. So what this is a definition problem. Let's move to the later part of the question. So it is saying that let there be a function chi. So chi is a function from the vertex set of the graph to the set of natural numbers from 1 to k. So such a function is called a coloring. So basically this function is assigning to every vertex in the graph some number between 1 and k. So that number can be thought of as a color. So let such a coloring be given of the vertices of the graph. Now let G dash be a subgraph of G which is colorful. So colorful, what does colorful mean? Colorful means that for an edge in G dash, the endpoints of the edge receive different colors. So then which of the following statements are correct? Okay. So what I will do, I will push this thing down so that we have the question as well as uh, the writing in one space. So yeah, so we have this graph which is G. I'm just taking an instance. So yeah, so let us say this is a graph. And for this graph, there is a proper coloring using K colors. So proper coloring means no two uh, adjacent vertices get the same color. So let's use some numbers. So if you give this one color 1, then its neighbor cannot get color 1. So it might get 2. But if this is 2, then none of its neighbors can get 2. So I'm just arbitrarily giving numbers. So this is 2, this can be 1, this can be 1. So 1, 2 are taken, so this cannot be 1, 2. So this is 3. So 1, 2, this can again take 3. Sorry, this can take 3. So this is proper coloring of the graph G. So let's call this G because for every edge, the endpoints of the edge got different colors, or in this case, numbers. So I hope I did not make any mistakes. Okay, so the question is saying that if you consider a subgraph G dash, so let us say this is part of a big, so let us say this is G dash. So let us say the graph was in fact bigger. The graph had more edges. So we're only looking at a subgraph of G dash. Then maybe there were violations. in the rest of the graph, that is none of our concern. So maybe 1 1 was there. So for this edge, there is a violation, or even for this edge, both the endpoints got the same color, so that is a violation. But within the subgraph, there is no such violation within the subgraph G dash. Okay, then we'll say that okay, G dash is colorful. Okay, so now we are going to look at these statements and we are going to decide which of them are true and which of them are false. So first is there are k to the power n possible colorings chi. So it is not x, it is actually chi. So how many possible colorings are there? That is the question. The first one is asking, let us mark them A, B, C. So first one is asking that how many possible colorings of G can exist. Okay. So any thoughts?
So since we have k number of the vertices in the subgraph and as well as in the tree which is isomorphic to the given subgraph, and for each node we have k number of the possibilities. So for each node we have k number of how many colors are there? Uh,
K.
K number of the colors, right? So
K colors are available.
uh-huh. And we have to only consider the k number of the vertices and not the uh, I mean, how many vertices are there in the originally given graph?
It is not given, is it? Okay, let us, sorry. This is, I have picked from NPTEL website. So let us say n vertices are there in G.
Yes. So, and what this x here is that there are k raised to the power n possible colorings x. So what this
Sky
x?
actually, it's sky. So how many functions are there?
Okay. Okay.
And I should make it more specific, I think. So this is not well formed. So there are k to the power possible coloring sky, and chi is defined on G. So of the vertices or vertex set, I should say, because chi is defined on the entire vertex set of G. So this is what the statement means, that there are k to the power n possible coloring sky of the vertex set of the original graph G.
Without violating the constraint or in general the total possible colorings.
In general,
So in general, it is true then k raised to the power n possible colorings would be there because for each node we can have k possibilities.
that is
We
true.
can, yeah.
That is correct. So I'll rephrase it for the sake of the other participants. So you have n vertices in the graph. So let us say the vertices are v1, v2, v3 up to vn. So now what does chi do? Chi assigns. So chi's job is to assign one color from the set 1, 2, 3 up to k. Okay. So let me just make some space. So for every vertex, so let us say for this vertex v1, you have how many choices of assigning a color? So there are k possible choices you have. For the second vertex, again, you have k possible choices. Third vertex, again, you have k possible colors. For all vertices, you have k possible colors. So by the theorem of multiplication, because these colorings are done independently, the total number of ways to color the vertices of the graph will be multiplication of these uh, ways of coloring vertices. So for every vertex, there are k ways. For so many vertices, n vertices, there are k to the power n ways, right? So we have just multiplied k n times. So this one is true. I'll just mark it true. Okay. So now let's go to the second one. So consider so what I will do, I'll just copy this and go below the page. So this is the statement for which we want to decide whether it is true or false. Oh, the entire thing got copied. Sorry. I think it should be possible to copy this to one. Okay. So this is our statement B, right? So we want to decide whether this is true or false. So consider a subset H of the vertex set, and H has k vertices. The number of colorings that are injective on S is at most. Okay, what is S? I made a mistake while copying now. This looks okay. Okay, so S is not defined. So I think there is a mistake in the question. Okay, I think we can just keep it parked. So we'll keep it pending because S is not defined. We'll go to the next one. I've copied this from the previous offering of this course assignments. This was there. So anyway, so let's H be a vertex subset of the vertex set having k vertices. The number of colorings that are injective on H, this is well defined, is at most this k factorial k to the n. So I'll just go down. So instead of S, we have H. So this is the third question. So what are we counting? So we're counting the number of colorings that are injected. So let us say that this is the entire vertex set. And in this vertex set, there is a smaller set, which is H, and mod H is K. So how many colorings are there that are injective on H? So injective means 1 to 1. Okay. So that is the question. So how many colors here? So you have to map all these vertices inside H to some color in this set. So you have k colors at your disposal. So you want to map every vertex. So because there are k vertices in H, so you want to map every vertex to one color, and you don't want to map two vertices to one color. Many one is not allowed. So you want to map, you want to get a one to one mapping. So every color should have a unique pre-image, right? So how many ways you can do that? That is the question. Okay, so this, this one is k factorial. So I'll just write this k factorial k to the n minus k. So this is it's nothing but just write k factorial after this, right? So k factorial times k to the n minus k. Okay, this is true. This is correct. Okay, fine. So how shall we do this?
So for each vertex in H, so for the first vertex in H, we have k number of the possibilities. And for the
Correct.
second vertex of the H, we have k minus 1 number of the possibilities. Because the
Yes,
mapping has to be 1 to 1. So
correct.
finally, we will reach till 1. So the value comes out to be the factorial of k. And this does not take into the consideration that the constraint has to be followed that no two vertices are going to have the same color, right?
Correct.
Because yeah, so if you don't take that into consideration, the value is factorial of k. But I don't know from where this term k raised to the power n minus k is coming into the picture, because then for the remaining vertices of the graph, is say, there we have the n minus k number of the remaining vertices, and which obviously can be assigned, say, in k raised to the power n minus k number of the ways.
That is right. So yeah, you have actually answered both parts of these two terms. So this term k to the n minus k is coming for the rest of the vertices which are not in H. So remember that they have defined coloring chi over all the vertices of the vertex set of G. So this is Vg to k. So therefore, and this statement is only insisting that once you have fixed H, the coloring for the vertices of H should be 1 to 1. But for the rest of the vertices in the vertex set, there is no such constraint. So for the vertices of H, as you have rightly observed, if you consider the first vertex of H, then there are k colors possible, k possible choices of colors for the first vertex. And then the one color is taken for the first vertex, and that color cannot be assigned to any other vertex in H. So then you look at the second vertex in H. For the second vertex, you have one less color in your disposal. So that way, for the vertices of H, you will have a total of k factorial colors. I mean, k factorial ways of coloring. And for the rest of the vertices, there is no restriction. So every vertex can be colored in possibly k ways. So how many vertices are left? N minus k vertices are left. So k gets multiplied n minus k times. So therefore, the total number of colors, colorings possible with this constraint is k to the n minus k times k factorial. Right. So this was a question that I picked from previous year's offering. So let's. So I think as you already correctly answered the question, so we can move to the next question. Right. So again, you have this k cardinality subset of vertex at H, which is fixed, and you want to calculate the probability that the vertices of H are colored with pairwise distinct colors. In fact, you want to find a lower bound on this probability. Okay. So the question, so let me just copy this, then we will analyze the probability. So this is question D. So it is saying that, okay, uh, you have this graph and you have this subgraph, I mean, subset of vertices. So this is H, this is the vertex set, and H has k vertices, and you have k colors in your disposal. So there are so many possible ways in which you can color the vertices. So what is the probability that the vertices of H are colored with pairwise distinct colors? So we have already seen that there are k to the power n ways of assigning colors to the vertices of G, k to the n ways of assigning colors to vertex set of G. So out of these colorings, we have to count those colorings for which the vertices of H are colored with pairwise distinct colors. So what does that mean? So let us say this is H. Okay. So in fact, we need not worry about the edges. So let us just draw the vertices that are in H inside here. So you want these vertices which are inside H to get distinct colors. Pairwise distinct means all the colors are distinct, right? Correct. So the probability is nothing but what is the probability we're counting? We're calculating. We're calculating the probability that the vertices of H receive distinct colors. Okay. So in the denominator we have k to the power n because there are k to the power n possible ways in which vertices of the entire graph G can be assigned colors. Now the question is, how do we find the numerator? So here, what is the numerator? Numerator is the count of, this is count of how many number of colorings where vertices of H receive distinct colors. Right. So we are interested in this quantity. So we're interested in this quantity. Okay, so because H has only k members, so if you are willing to give distinct colors to the members of H, so you give the first vertex of H, let us say a color red. Just mark, let me mark these vertices. So let us say we mark the vertices of H as E1, E2 up to UK. So we give E1 color. So some coloring gave E1 color to uh, the first vertex of H. Then you are left with, for U2, then you are left with only k minus 1 colors. In fact, it is a analogous argument. In fact, same argument that we have seen in the previous case. So for the first vertex, you have k possibilities. For the second vertex, if you want to make sure that the second vertex is not getting the color of the first vertex, you have k minus 1 possibilities and so on. So to make sure that the vertices of H receive distinct colors, there are k factorial ways of ensuring that. And the rest of the vertices, of course, the coloring is also defined on the rest of the vertices. For them, you have k choices for each of them. So k to the power n minus k. So that is the quantity we already saw, and that is the quantity that will go to the numerator. So this will come out to be, so this thing, I'll just write it down. So this is in the numerator, and below we have k to the power n. So this is nothing but, so now we compare that, are these two things, how similar are these? So in the denominator we have k to the power n, in the numerator we have k to the n minus k, k to the n minus k is also matching, but in the numerator we have something like k by epsilon, k by e. So e is the base of the natural logarithm, k to the power e to the k, whereas we have k factorial. So there is a result which we have seen in the videos that k factorial is at least k by e to the power k. So I'll use that, and that will give us a lower bound. So instead of k factorial, we will replace k factorial by k by e to the power k, and rest of the things will remain the same. So that will give us a lower bound. In fact, that is what we are interested in, at least. So the probability that the vertices of H are colored with pairwise distinct colors, exact probability is this, but after replacing k factorial by this, we get that the lower bound on the probability is this, right? So why this is true, this I will leave up to you to verify that this is true. And if you cannot find out why this is true, then we can look at the proof of this in the next session. So this will mark this as true. Okay, so the previous one is also true that we have seen, right? Okay, so move to the next one. So what I planned today is because it's a 2-hour session, it gets a bit demanding for both you and me. So we'll take a 5 minutes break after 1 hour of this session. So let's finish this question. After that, we can take a break of 5 minutes. Okay, so we are now looking at the statement E. So now we are in the domain of tree subgraph isomorphism problem. So let T, so let T be rooted at R. So T is at tree, which is part of the input. So the input has tree T on k vertices and an undirected graph on n vertices. Okay, so let T be rooted at R, and T sub x denote the subtree rooted at any vertex x of the tree. Okay, then for every x in the vertex set of the tree and every vertex of the vertex set of the graph, and for every subset of the k colors, such that mod s. Okay, what is mod s? Okay, s is a subset of colors. So, so S is sort of the colors that we can use, let us say. So mod S is one less than the number of vertices in the subtree rooted at Tx. So we define a Boolean variable corresponding to these things. So the Boolean value is tree S comma X comma V. So S is the set of colors that is at our disposal. X is a vertex within the tree that is uh, we are concerned with the vertex in the tree, and V is the vertex in the graph. And this Boolean variable is set equal to true if there is a colorful tree rooted at V isomorphic to Tx with vertices colored with all colors from S. Okay, so what is the definition of colorful? Definition of colorful is that every edge in the tree has distinctly colored endpoints. So for every edge, the two endpoints get different colors. In that case, we say that it is a proper coloring, or they are saying it colorful. Okay, so the point to focus on is the definition of this Boolean value. So this is equal to true only if there is a colorful tree rooted at V isomorphic to Tx with vertices colored with all colors from S. Okay, then tree S x comma V is false if, okay, so this is okay, so this is the statement. We have to decide whether this is true or false. So tree S x comma V is false if chi of V is in the color set. Okay, so this is a bit, I would say, a bit dense question. So let us draw a diagram to understand all that has been described here. So what I will do is I'll just copy this thing, just copy this statement. So I'm copying. Copy. Okay, so let me try to draw a diagram to illustrate what is going on. So we have defined a Boolean variable tree that is defined on a subset of colors, a vertex X. So this one is belongs this one, that vertex belongs to the tree, and V belongs to the vertex set of G. So this Boolean variable is defined to be true when if uh, there is a colorful tree rooted at V. Okay, so what I will do is I will make some space. This is defined to be true if there exists a colorful tree rooted at V, isomorphic to T of X. So T of X is a subgraph rooted at X. So there is a colorful tree rooted at V, isomorphic to Tx. And additionally, this colorful tree has all the colors, and all vertices of this tree are colored. The vertices of the tree colored with the colors in S, with all the colors. In fact, all the colors have to be used. Okay. And if that is not the case, otherwise this is false. Otherwise. So now we are interested in deciding whether this statement is true or false. So what is this statement saying? So this is saying that the color assigned to V. So let me do one thing. Let me draw an example graph. So let us say this is the graph, right? And let us say this is V. And there is a rooted, there is a tree also. So this is T, this is G. Let us say, I'm just making up this thing. So, right, so let us say this is X. So X is inside T. So X is a vertex in T and V is a vertex in G. So what is Tx? So Tx is this portion, the subtree rooted at X. So this is Tx. So let me mark this. So this part is T of X, or rather T sub X. Okay. So now we are asking, so what is S? S is a subset of colors. So let us give the colors to the vertices. So let us say this is the coloring. Okay, this is 2, then this is 3. And this is 1, 2. This can be 1. This can be 2. And this can be 3. I hope I haven't made any mistakes. So now we are asking what is tree of, so what is S? So we have to define S. So let us say S is, let us say S is 1, 2. now we want to ask what is tree s comma x comma b. So what is this? What are we asking? So we're asking this: does there exist a colorful tree rooted at v? Okay, which is isomorphic to this tx, and all vertices of tx, no, all vertices of this colorful tree uh, have colors from S only. So in this case, do you see any colorful tree rooted at V which is isomorphic to this? So first thing is that this has only, yeah, you wanted to say something?
Yes, so what is the cardinality of the S here? So the cardinality of S is that the cardinality of VTX. So the number of the vertices in this tree T and minus one.
Oh, sorry,
So
sorry.
so
Five. So
one,
I
two,
have to
three, four,
take some
five.
more colors. I was just making up numbers. So you were right. Makes sense. So you have found a bug. So we fix the bug. Yes. So we have this additional condition that you are having uh, one less than the you're having how many colors? One less than the number of vertices in Tx. So now we have a well-defined question. So can
But
we?
still I'm not clear with this that what this chi of V is the element of S indicates. That when the value of this boolean is false.
Oh, this indicates that the color set, the set of colors which is in S, V is colored using one of the colors in S. So if V was 5, then that would be false. So here S is only 4 colors, 1, 2, 3, 4, and chi of V belongs to S means that V is colored with one of these 4 colors only.
So clearly the V would be colored with one of the color in S. So every time this Boolean expression will result into a false value.
Correct. So as you have rightly observed, so this is saying that because already we have taken the color uh, in S, so we are left with one less color. So yeah, I mean, I will make it more formal. So you have used one color in S. So how many colors you are left with? You are left with mod S minus one color. But mod S minus one is what? So this is P of Tx minus one minus one. So you are left with P of Tx minus two colors. So there is no way you can color. So what is the size of the subtree that we are looking at? The size of the subtree has to be mod Tx. So the subtree is rooted at V. So V is given a color. So now you're left with mod Tx minus one vertices. And these many vertices you want to color using only the vertex set of Tx minus two colors. I mean, the notation is slightly. So by mod Tx, I mean the number of vertices of Tx. So I'll just. Yes, so you have mod Tx minus one vertices. One of the colors is already used. Now you are left with these many colors. So for at least two vertices in this subgraph rooted at V, you will be forced to use the same color. So therefore, the statement will, the colorful tree cannot be obtained, and thus this expression will evaluate to false immediately.
No, it's not clear actually. So when the value of this tree is true, and when will it become false? So if we can find a mapping of what? Mapping of what you wrote here in the explanation, that if there exists a colorful tree rooted
Yes,
at the vertex V is
yes.
isomorphic to the TX, then its value is true, and its value would be false, not otherwise. But then some condition is given here
No,
that
no,
the
no.
chi of V is an element of S.
This one is separate. So this entire thing is corresponding to the true case.
Yes. So, so my question is that what happens? What actually happens when this chi of V becomes the element of S? And I mean, so what's the meaning of the term the chi of V?
Chi of V is the color assigned to the vertex V using the coloring chi. So chi is a function. It colors all the vertices,
Mhm.
and maybe there are more colors in your disposal than the set of colors. In fact, it is written that totally there are k colors which are used to color the vertices of the graph G.
Uh-huh.
But some of the colors you are picking and calling them S. Now, chi V belongs to S means that you have used a color from S to color the vertex V.
Color of the okay, okay. So okay, so but then whatever color we select or whatever mapping we select, ultimately
Yes.
would belong to S only. So that is what my apprehension here is. So in
In
which
this,
case, so what could be that case wherein X of V does not belong to S? Can we find any such case wherein the mapping of the color to the vertex B does not
yes.
belong to S?
So let us say in this example, instead of coloring the vertex V using the color 1 or 2 or 3 or 4, we
Mhm.
colored it using 5. That is a valid coloring. So instead of
Yes.
1, so let us say chi is a function that colors the vertex V with color 5, then that is a valid coloring.
Mhm.
Then the chi of V is 5, but it does not belong to S. So chi of V does not belong to S in this case because S is only 1, 2, 3, 4, 5. Not 5, 1, 2, 3, 4 only. So you have given 5 to this, so therefore chi of V is not belonging to S.
Okay, so then how many colors are available to
K
paint
colors
the?
are available. K colors are available.
Okay,
So
okay.
K is some number. Let us say here K is 6,
Mhm.
but S is a subset of K.
Fine. So S is a subset of
1, 2, 3, 4, 5, 6, 7 up to K. So this
yes.
notation, so this notation means the set 1, 2, 3 up to K. So all the first K natural numbers is not denoted by K within square brackets.
Correct. And K minus 1 vertices are there in the VTX. Does this mean so? That if we have picked K number of the colors, then there has to be K minus 1 number of the vertices in the tree TX. I mean, what this equality here indicates that the mod of S is equal to the mod of VTX minus 1. This is so very, difficult
Okay,
to understand. Yeah.
so you have a tree to start with in the definition of the problem.
Hmm.
So where did I define the problem? Yes, so this is the subgraph isomorphism problem.
Hmm.
So you have a graph, and the graph has, let us say, n vertices, but the
Hmm.
tree has k vertices.
Hmm.
And you are asking whether there exists a subgraph in G that is isomorphic to T.
Right.
That is the question. Now, to solve this question, there are certain sub-steps. So here there is a randomized algorithm which does a coloring based argument. So now, hello,
Yes.
yes. So now we are looking at this question, which is independent of that problem. So here
Mhm.
we are saying that okay, you have T, but for every vertex in T, you are going to define T sub that vertex as the subtree rooted at that vertex. So so for every x, you have a T sub x, which is the subtree rooted at x. Now,
Right.
the number of vertices in that subtree for a given x is known to you. Now you define S to be uh, one less than the number of vertices in this subtree.
Yes.
And now it is not known that what is the coloring, whether the coloring is of the graph is using only modest colors or more than modest colors. So here modest in this example is 4, but
Mhm.
whereas it is maybe the graph was having too many other vertices and edges, and in fact 5 colors were used to color the vertices of the graph. That is possible. So
Yes.
depending on what the coloring is for a
Mhm.
given vertex V, we will be able to answer whether the color of that vertex belongs to S or not.
Okay. Okay. So does this mean that now the coloring of the vertices within this graph G will start from 5 onwards and it can never be 1, 2, 3, and 4? So the coloring would be like this, that you assign the color to one vertex as 5, the other one as 6, and till 7. So
Mhm.
now say if the cardinality of this VTX is K, so then K say is its cardinality is say P, then K minus P number of the colors are available to paint the vertices of the graph G.
The question is not inferring to such a statement
Because
that
if the
one.
value of the chi of V belongs to S, then the value of this Boolean expression will become a false value, will return
Correct,
false.
exactly. That is
Yes.
true. You have this will become false as soon as you identify that V is colored using one of the colors of S, then
Huh.
there is no way to color all the vertices rooted at
V.
V
Hmm.
by while not violating that constraint, because you
Yes.
don't you don't want to give same color within the subgraph. You want to give
Right.
distinct colors.
Right. So let us take the value of k is equal to 10. So
Okay.
if k is equal to 10, and since there are, say, let us take the value of k is equal to 11 instead of 10, otherwise we'll get the same value as v minus k. So say if k is equal to 11, and now the cardinality of this VTX is 1, 2, 3, 4, 5. So therefore, the number of the elements in S are 4. So therefore, we are left with 11 minus 4, 7 number of the colors which can be used to paint the vertices of the graph G to enable to make this tree expression a true value.
Okay.
And so do we have to check that whether the colorful tree rooted at the vertex V, wherein we can use the 7 number of the colors, is isomorphic to the TX, which can be painted with only 4 number of the colors.
So you are saying that if K is 11,
Mhm.
then in spite of the fact that the color of V is not within S, it
Mhm.
might still evaluate to true. That's what you're saying?
Yes.
Okay.
Because to evaluate this expression as true, the colors of the vertices of the graph G and the vertices of the tree X should be different.
Yes. So what is k? Is k 11 possible? So k is initially they're saying that a tree t. So the number of k is nothing but the number of vertices of t. Anyway, so we did not. So here it is. So if you read the first initial paragraph of the statement, then they're saying that the tree is on k vertices. So k is
Yeah.
fixed to start with.
Yes.
Okay.
So okay. So like in this case, how many vertices are there in T? If you go below to this diagram, yes. So there are 1, 2, 3, 4, 4, and then 5, 9.
No, there
So
is, yeah, probably we can make it even 11 if you like.
yes, yes, 11. So now there are 11. Yes. So
Yes.
so yeah. So we have to we have to search for this possibility, that whether its value is true or false, I think.
Okay, so let me give it a thought.
Mhm.
So we want to find a colorful tree rooted at V, which is isomorphic to T sub x, and all vertices of this isomorphic tree should be colored using colors in S. So my initial understanding was this, that let's just make it slightly smaller. So my initial understanding was this, that as soon as you colored V using a color in S, so you are losing one color. You are losing one color, so you are left with mod S minus one colors. Sorry, no, high mod S. Uh, so what you were saying, that there is not mod S but K colors. So you're left with K colors. That's what you were saying, not mod S. So there might be a situation that even after V was colored using a color in S, still this expression might be true. Just give me a minute. Chi of V belongs to S. You want to color distinctly. So yeah, I mean, if you consider that after you color the vertex V using a color in S, then if you are saying that okay, mod S minus one colors are left, then probably we can immediately say that okay, then there is no way tree of S x comma V can evaluate to true, and therefore it will be false. But if k minus one colors are left and k is a very large number, as you have uh, pointed out, then I'm not really sure,
So
because
what do we want to show here actually? Can you go back to the question and see what do we want to is false? Okay. So n is false if xb is the element of yes, yes. Mhm.
So yeah, I mean, because K is the cardinality of the vertex set of T,
Mhm.
then I don't see why K can't be very large. Because they started with this statement that a tree T on K vertices.
Mhm.
So K could be very large, and in that case, we will have so many colors in our disposal. So maybe we have to understand this algorithm. Basically, the algorithm is to decide whether there exists a subgraph in the graph underrated graph G, which is isomorphic to T. So therefore, it is natural to have some bound on T. Of course, I mean the natural thing is N is definitely at least K.
Yes, yes.
Maybe there are some other bounds on this. So they're doing some random coloring and they're able to show an algorithm that is able to answer this question with high probability. So I have to probably get back to you on this after reading the material once again.
Yeah, sure, sure, sure. Or rather, we can skip this entire question because I think that the remaining parts are also maybe related to this thing
Right, right,
only.
right. We have to
Yeah,
probably get back to this in the next session.
yeah, sure, sure.
Okay, so I'll encourage all of you to watch the video or read from the book this tree subgraph isomorphism problem and the randomized algorithm for this problem.
Mhm.
And then we'll look at this once again. So, fine. So, is it fine if we take a 5 minutes break because it's already
Yes, yes.
7:20?
Yeah, that is required. Yeah,
Okay,
thanks.
all right, fine. Hello, are we back?
Yes, yes.
Okay. Okay, so I'll give you a minute or so to read this question. Uh, so this is basically looking at two quantities in graph theory called omega g and chi g. So chi g is the chromatic number and omega g is the size of the maximum clique, the clique number in a graph. So for example, here is a graph. So in this graph, there are five vertices and there is no triangle, therefore the maximum clique size is only 2. So if this is G, then the clique number of this graph is only 2. But what is the minimum number of colors that we can assign to the vertices of this graph such that the endpoints of every edge receive distinct colors?
So that is 3.
Correct. So if we color this with A, then these two neighbors will get B. Then this can again get A. But then for this vertex, both A and B are forbidden. So three colors are necessary for an odd cycle where uh, for an odd cycle, two colors will not suffice. So well known result. So chi for this graph is 3. But for those graphs for which the clique number is exactly equal to the chromatic number, such graphs are called perfect graphs. So the question is asking, what is the relationship between chi g and omega g? Is it greater than equal to or less than equal to?
So since we are not talking about the perfect graphs now, graph could be any graph. So then the first option is clearly correct, that the chi of g is greater than or equals to the omega of g.
Yes. So in a graph, if there is a clique of size omega, so let us say this is a clique, I mean, I'm not drawing all the edges, but yeah, so omega vertices are involved. Then each of the vertices have to receive distinct colors because there is an edge between every pair of vertices. So at least omega colors are definitely required. So chi g is definitely at least omega g. So this one is true. Oh, sorry. So the number of colors is at least the number of vertices in the clique, max clique in the graph. So therefore, this statement is the opposite of this. So this is false. Right. So C47 means it's a cycle on 47 vertices. So it's an odd cycle. It's an odd cycle. In an odd cycle, oh, we are looking at the clique number. So what is the largest clique?
So since it is a cycle only, so every vertex would be connected to at most exactly 2 vertices.
Correct. So there are no triangles. Because there are
Yes.
no triangles, so omega cannot be 3. But there is edge. So edge means that is a clique on two vertices. So the next statement that the omega of C47 is 2, this is true.
Yes.
Now is C47 a perfect graph?
No. No.
Yes. So because it's an odd cycle, so therefore the chromatic number is 3. Whereas we have seen that the clique number is only 2. So these two do not match. Therefore, C47 is not a perfect graph. But is C48 a perfect graph?
So if we have even cycle, then what will happen? 4. So then we require, so this will become a closed one.
Right. So if you number the vertices 1 to n, let us say even, let us say 2n, then you give one color to the odd numbered vertices and another color to the even numbered vertices in the cycle.
Yes.
So then what will happen? So every, yeah, go ahead.
Yeah, so then the chromatic would be same as the click thing.
Yes. So every odd numbered vertex is neighbor to even numbered vertices only, and every even numbered vertex is neighbor to odd numbered vertex only. Therefore, it is a proper coloring, and two colors will be sufficient for an even cycle. So chi g will be only 2, and omega g we have seen because it is a cycle, it does not have any triangles. It's a cycle means it's a large cycle, not a triangle. Therefore, omega g is also 2. Therefore, the chi and omega values are same. So it is a perfect graph. So this statement is true. So now next one is saying bipartite graphs, empty graphs, and complete graphs are all perfect graphs. So let me draw a bipartite graph. There is a, let us say this is a bipartite graph. Some vertices, and edges are between vertices of two parts only. So there are no edges between vertices in the same part. So such edges are not there. Such kind of edges are not there. So what is the chi value for this?
So and can we connect one vertex in the right hand side to two vertices in the in the left hand side?
Yes.
Okay. So say in the worst case scenario, when all the vertices of A are connected to a single vertex of the B,
Yes.
then we would be requiring how many colors? So we require one color here, and then uh, yeah, so
So
three
let us
colors.
say,
Three colors are sufficient.
on both sides there are k vertices. So k vertices in the A side and
Mm-hmm.
k vertices on the B side.
Mm-hmm.
Now, let us say the first vertex of A is connected to every vertex of B.
Mm-hmm.
Then how many colors are you going to use?
K number of the colors.
Uh, why is that so?
So if every vertex of A is connected to all vertices of the B,
Okay.
then to follow the constraint, the color in between a vertex of the A and all the vertices of B should be distinct. And then we have the k number of the vertices in B. So therefore we require k number of the colors and plus one, k plus one number of the colors.
No, so the constraint is in the graph G, in G,
Mm-hmm.
every edge u comma b, u comma v, if you see, if u comma v is an edge, then
Mm-hmm.
the color of u must be different from the color of v. That's all. That is the constraint.
Yes, but then in the worst case scenario, a single vertex of the A could be connected to all the vertices of the B. Is this possible?
Absolutely. So let us just make it more concrete and let us say k is 3. So 1, 2, 3 vertices, 1 dash, 2 dash, 3 dash, 3 vertices. So let us say 1 is connected to everybody. on the other side.
Mhm.
So you give one a color. Let us say you give one a color red. So
Yes.
then you cannot give red to any of the vertices in B. So you give them a color green. So
Yes,
this can
yes.
get green, this can get
Yeah,
green, this
so
can get.
yeah, yeah. So I require two colors.
Yes. Because there
Mhm.
is no edge between the vertices in part B and there is
Yes.
no edge between the vertices in part A. That is the definition. On the other
Ye-
hand, all the vertices in part A can get the same color.
Yes, yes.
The edges are only between part A and part B. So number of colors is exactly two.
Right.
So two colors will suffice. But what is the clique size, maximum clique size? Omega G.
So that is two because two
Yes,
vertices are.
there is no triangle in this graph. By definition of bipartite graph, only even cycles can exist because there are no odd cycles. Therefore, there is no triangle. Therefore, there can be only edges. Maximum clique could be an edge which is having two vertices. Therefore, bipartite graphs are definitely perfect graphs. What
Yes.
about empty graphs?
So in empty, that is same. The at least the chi of g would be same as the omega of g.
Yes. So empty graph means there is no vertex, no edge. It is just a placeholder. So chi of g is trivially 0 and omega of g is also trivially 0. So that is also equality exists. And how about a complete graph means all the
That would be same, yeah. Every vertex is connected to every other vertex. So
right. So what is the chi of a graph? Let us say kn, n vertices complete graph.
So if there are n vertices in this graph, so I require n number of the colors.
Exactly. And omega kn is by definition n. So
Yes.
therefore, this is also a perfect graph. So this statement turns out to be true. Okay. So now this is the last statement is complement of a perfect graph is a perfect graph. So complement means that if there is an edge between u comma v, then in the complement there is no edge between u and v. And if there is no edge between u and v, then in the complement there is an edge between u and v. So for example, this is let us say g, then the complement of g is all the diagonals I have drawn.
Hmm. So yeah. So here it seems that the statement is true. Uh, statement is true, and moreover, if I take the complement of a complete graph, then I'll get all disconnected nodes. So then the scenario would be somewhat similar to the empty graphs. So since empty graph is also complete, so yeah, so I think that this last one is true.
Yes,
But I do not have enough evidence to say a true statement.
that is true. Yeah. So yeah, you're right. For example, we know that C48 is a perfect graph. So all uh, even cycles are perfect graphs because this is not an even cycle. Uh, Let me draw an even cycle. So an even cycle is two colorable, and the maximum click size is also two. So but even cycle is a perfect graph. But if you draw all the diagonals of this hexagon, then you will be drawing 9, edges. Is there a simple way to see that the complement of this graph is a perfect graph?
So, the complement of, I can say one thing, that the complement of a click, to what extent is this true? That will the complement of a click be an independent set? So, not sure. I don't know.
Complement of a clique. So you mean clique means so you are saying that there is a clique as a subgraph in a graph.
Mhm.
I'm not sure what is you are saying. Complement.
So since in the click, the every vertex is connected to every other vertex. It is a
Yes.
subgraph. So the maximum subgraph wherein every vertex is connected to every other vertex. Uh, let us consider the max click, say. So then what the independent set be? That none of the vertex is connected to the other vertex in that subset. So will this be viewed as a complement of the click? Because getting the click of a graph is same as getting the independent set of the inverse of the graph. I don't know.
This is the inverse of a graph.
Inverse of a graph means that whenever you have connectivity in the original graph, so make it disconnected, and wherever
Oh,
you
you
have,
mean complement. That is what is
yes,
called complement.
yes. So the complement of a click is this. I don't know whether it's technically
The
true or not.
complement.
Yeah, please continue. Complement of
So
a click is same as independent set. No, no.
complement of a clique will be empty because all the edges will be deleted. I think what you are referring to is the vertex cover and independent set relationship. The complement of vertex cover that would be an independent set.
Is this?
Just a second.
So what is the correct answer for this option? Whether the complement of a perfect is a perfect or not?
The answer is true,
Okay, okay.
but there is no simple way to see this. For example,
Yes.
this is a this hexagon. This six cycle is a perfect graph, and if you
Mhm.
draw all the nine diagonals, it sort of looks like a star. But I don't see why immediately it would be a perfect graph. You understand?
Yes, yes, yes.
So in this case, what is the chi of g dash and what is the omega of g dash? Let me give it some colors. So one is red. So three cannot be red. Four and five cannot be red. So two on the other hand can be red. Six on the other hand can be red. And no,
Four,
six.
four.
No, sorry, six can be red. Six and two are connected. Uh, so we need a different color for three and four, and we need a different color for five and six also. Yeah, so I think this is sufficient. So three colors should be sufficient. And there is no K4. So omega G is G dash is also 3 because there is a triangle only. So this is called the perfect graph theorem. The last thing is called, if you Google search, this is called the perfect graph theorem, and the proof is given by Lovash. It is a non-trivial proof.
Okay, okay.
So we'll not look. I mean, we don't have time, or I mean, this itself will take 2 hours to explain the proof. So you
Mhm.
can look it up. So this was on perfect graph. So let's look at one more question because we have 10 or 12 minutes. So in fact, there was one more question, but we'll just look at one question today. This is the last question for today. So this is based on the lecture 17. So if you haven't watched lecture 17, then I'll give you some background. So you want to find the longest path in a graph. So we know that we can find the shortest path in a graph. So we have Dijkstra's algorithm for that. So this is a polynomial time solvable problem. But the longest path, that means the path having the maximum number of edges, this problem is NP hard. The longest path in the sense a path, let us say, consisting of vertices. So there is an edge between every consecutive vertex, and there are no repeated edges. So P I J is, I mean, it's not P I J. So every index is distinct. So I K is different from I J for all J different from K. So for this problem, there is a randomized algorithm which requires this dynamic programming module. So what they do is they randomly, so they decide a value of, okay, so the question is, does there exist a longest path of size at least 3? So K is given to be 3. So does there exist longest path of size at least 3? So what they, so as we can see that this is true in this graph, but for large graphs, what they do is the following. They color the vertices of the graph uniformly at random using K colors. So for every vertex, they make a random decision to give one of the K colors to this vertex. In this case, there are 3 colors, let us say red, blue, and orange. And now you have this graph. Each of the vertices have received one of the colors, red, blue, and orange, and this has been done uniformly at random. So now we form this DP table. Okay, so this DP table, I will define the entry of each DP. I think I have it somewhere. Right. So DP, these values are missing. We're supposed to find these missing values. So DP corresponding to red and B3. So what does this mean? So this entry B3 and red, this means this is asking that does there exist? I mean, this is equal to 1. I should write it in the, so this would be equal to 1 if there exists a path ending at P3, okay, and P3 is colored red. So this is the meaning of this entry. So is this true or false?
So the color of the vertex V3 is red. So there exists a path ending at V3 and the V3 is colored red. Yes, so there is a path. Say if we make a move from, is it necessary that we need to make we need to start the journey from V1 only
No,
or
no, no. That is not necessary.
not?
We have to just show that okay, there is a path that ends at
Yes,
V3 and V3 is red. So this value is true. So we'll mark
yes.
this as 1. This is done. So similarly, uh, what is TP of blue comma V5, which is not, which is very interested in this thing. So does there exist a path that ends at V5 and V5 is blue? That is the question.
So if the color of the V5 is not blue, then no path which is ending at the V5 can ever have, its ending point with the blue color. So I do not find any point in defining this in this way, that does there exist a path ending at the vertex V5 and the color of the V5 is blue. We can straightway say that does the color of the vertex V5 is blue or not.
Yes. Yeah, it is a base case. So uh, it will become more clear when we look at the uh, table entries later in the table.
Okay, okay.
So for example, we do not know that entry corresponding to red, blue, orange, and V3. So this entry is not known. So
Yes.
this is asking that does there exist a path? This is equal to 1 if I should write that way. So this is equal to 1 if there exists a path ending at V3 and V3 is red and and one V3. See, V3 is red. So V3 is red means now you are asking and the value of the entry V3 is already gone. No. So wait. V3 is red. I shouldn't say this. Just a second. Let me verify what this the way they defined. Okay, so not V3 is not red. Fine. Okay, so does there exist a path ending in V3 and dp of dp of the color set? Okay, so let us say C is the color set. So C is red, blue, orange. So dp of C minus the color of V3, comma, so neighbor of V3 is equal to 1. Okay, one of the neighbors, not all neighbors. So it means that you have a path using ending at V3. So let me just mark it. So this is saying that you have a path ending at V3, and because V3 is red and you are interested in finding a path having distinct colors, so you cannot use the color of V3 again. And then you are asking that is there a path ending at the neighbor of V3 that does not use the color with which V3 is colored? So does there exist a path ending at one of the neighbors of V3 that does not use the color assigned to V3? That is the question it is asking. So for
Yes,
V3, yeah,
but then why are we writing blue and orange here?
which
So
one?
had there been the different values like say red, comma green, comma orange, and then B3, then its value would also have been true only.
No,
So
so
what's the significance of blue and orange here then?
So green cannot come into the picture because the coloring which is done, the vertices are colored using three colors only. K is given
Yes.
to be three. So these three colors are predetermined to be red, blue, and orange. You can
Yes.
predetermine it to be something else. But you have three colors at your disposal, and randomly the vertices are colored using these three colors.
Yes. So what the value of the DP? Red, comma, orange, comma, blue, comma, V3.
Yes, so this is corresponding. So basically, this is asking the question, then does there exist a path ending at V3,
Mm-hmm.
and so the one condition is the path has to end at V3, and
Mm-hmm.
the other condition is another path has to exist that ends at one of the neighbors of V3, and that path won't use the color assigned to V3.
Right. So then what is the use of the remaining two colors here, blue and orange? They are not coming anywhere, appearing anywhere in this interpretation.
Yes, it will come into the picture. So for example, here you can see that the neighborhood of V3 consists of two vertices V2 and V4.
Mm-hmm.
So what is the color of V2?
Color of V2 is red.
The color of V2 is red. So therefore,
Mm-hmm.
when we are asking the question, does there exist a path ending at V2 that does not use in the color assigned to V3, then that answer is immediately no. So that cannot exist because V2 itself is red. So any path that ends at V2 is actually using the color red. So red is not allowed. See, once you have decided that V3 is red, then you are asking that does there exist a path of total size 3? So we're interested in the longest path problem. If you watch the video, it will become clear. So we are interested in the longest path problem. So we are interested in finding a path where every vertex gets distinct color. Now V3 itself has got red. So if there is a path ending at V3 of size of length 3, then that must mean that there is a path ending at one of the neighbors of V3 of size 2, and that path itself is also consisting of distinctly colored vertices.
Yes, that's true. So my only query was related to the appearance of the colors blue and orange here, and
No,
but
so
this interpretation is clear to me.
yes, now because the color of V2 is red,
Mm-hmm.
therefore the path we are looking for cannot come via V2 to V3. It has to come via V4 at. So because what is the color of V4? V4 is orange.
Mm-hmm.
Then we will set this DP value to true if the entry corresponding to V4, and now at our disposal we do not have red because V3 is already red. So we have
Mm-hmm.
orange and blue. That means we are allowed to have in the rest of the path the colors orange and red only, and we are allowed to have that rest of the path end at V4. So is this entry 1? If this entry is 1, then this entry will also be set to 1.
Okay,
You
yes,
understand?
now I understood. Then in the remaining calculation, we look for the DP of, since the color of X4, V4 is orange. So next we will look for the DP of the blue to the neighbor of the vertex V4.
Exactly.
And the neighbor, yeah, is this correct?
Correct, correct. That is what it is.
Yeah, yeah. Now I understood.
So now can you tell me whether DP of red, blue, orange, comma V3 will evaluate to 1 or 0? So you
Yes,
just have to
so
look up the table.
yes, yes. So now I look for the neighbor of the V4, and this is V5. And since orange has already been occupied, so therefore its final value would be equals to 0.
Okay, so where are we? So let me
No, no,
just.
no. But then the neighbor of V4, V2 can also be the neighbor uh, of the V4, right?
Hmm.
But if I follow this interpretation, so since the color of V4 is orange and okay, red has already been occupied. Perfect. So yeah, so its value would be equals to 0 then.
So the the entry that I am highlighting is corresponding to V2 blue and orange. This is 0. So that means a path via V2 cannot cannot uh, end at V3 using distinct colors only. And
Yes.
V4 is also 0. That means a path via V4 cannot end at V3 using distinct colors only.
Mhm.
Okay, therefore this entry will become 0.
Yes.
We'll set it to 0. Now we are left with only last this entry. And if you can solve this entry, then you have understood what we are talking. So let's just do one thing. Delete these things and put these things slightly down. Pull this table slightly down. Okay. All right. So we are asking the questions of what is the DP table entry corresponding to red, blue, orange, comma, V5.
Yes. So the color of V5 is orange. So then I look for its neighbors, uh, which can have the value red or blue. So say
Yes.
I go for V2, and then I look for the neighbors of B2 whose color could be blue. So I do not find any blue color neighbor here. So then I probably make a backtrack and then look for the neighbor of the V5 as
No, no,
V6.
wait. So we are looking at the neighbor of V5. Okay. So V5 has a neighbor V2. You're looking at V2. So
And
V2 cannot use orange, but it can use red and blue, right?
yes,
So I'm highlighting that cell.
yes,
So this is already one.
yes, this is one.
So we have found a perfectly
Yes,
distinct path.
yes. 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 So, but then how did they get this value as one that the dp of red comma blue on the vertex v2 is
This
1?
one. So this one
Yes.
would be coming again. So you're looking at the neighbor of V2. So V2's color is red. So V2 has
Uh-huh.
so many neighbors.
Uh-huh.
So if you want, so look at V1. So V1 is orange. So V1
Mhm.
comma orange is 1. So this implies, so from this we have got this.
Yes. What's the significance of blue here? If we are coming from the orange side, it's true that the color of the vertex v2 is red, but we are moving to v2
Oh,
either
okay.
from
Sorry. This is, I made a mistake. So you want blue, right? So fine. Uh, V2 is red. Oh, V6 is the one. So V6 is the one. So consider this. And I am sorry. From here we get this.
Mhm. Yes, from here we'll get this. Yeah, no, it's right.
Okay, sorry. I made a
Yes,
mistake. Okay.
yeah. Now I understood this table. It is somewhat similar to the dynamic programming tables we used to construct.
Exactly.
Some, yeah.
So you want to find a value, then you only look at some of the already calculated values and make a decision.
Yes. Yeah.
Okay. So fine. Thank you for joining. It was a nice interaction with you, and I hope that you will join next time again.
Yeah, sure. Thank
Yeah.
you so very much, and I learned a lot from this discussion. Thank you so much.
All right. All
And
right.
in the next week, what would you be covering? The week 5 or week 4 only? Which week would you cover so that I see all the videos in advance?
So this is, we covered week 4. So week 5 videos are out. So next week we can cover week 5, or if you have any questions from the previous weeks, then we can discuss them, but I'll primarily focus on week 5.
Okay, all right. Yeah. Thank you so very much,
All
and
right,
good
sir.
night.
Thank you. Good night. Thanks for joining.